Also, hey everyone, how are we doing? We'll see if we got people in the chat. Let's wake up Mubot here. Mubot's gonna wake up. We're gonna get some work done. Woo, busy day, busy day. Let's see. Ooh, lots of crazy stuff. There we go. Lots going on. Wow, lots going on. Is anyone in the chat yet? Want to study anything? Want to learn some material? Learn some material, get some studying done. My hair. It's time for a haircut, I think. It's getting pretty long. Time for a haircut. Well, we could do chapter 6 quiz. If anyone is here, maybe I'll post like holding office hours right now. Let's do that. Let's go to the Discord. Say office hours happening currently. And maybe we'll, there we go. And say need help studying office hours. Office hours, online office hours. Online office hours. Need help studying. Or happening now. Happening now. Online office hours. Join in to review or get help. And click here. And here we go. Here we go. Here we go. Here we go. Okay. There we go. So with that, we are working away. A little chill music right here. I don't want to get copyright claimed again. We didn't get copyright claimed. We got copyrighted. Not badly, though. If you're in the chat, feel free to say hi. We'll start doing some work here. We'll see if anyone joins in, says hi. Looking over assignments. Oh, that's nothing. It's so crazy when it shows up. Looking through assignments. Seeing if there's any problems. Getting things done. Who all is here? In about 2 or 3 minutes, if no one joins in, I'll start doing some work. Doing some work. Why is this one not loading in? So many. Nice. Yeesh. Get some work done in a moment here. Hey, what's up, Liz? What do you want to do? Mubot should be in the chat. Is Mubot awake? He is awake. Liz, good to see you there. What do you want to do work-wise? He is awake, right? He is there. Let's do some points for being here. Points for being here. What should we do? What should we do? Anything exam-related. I like that. I like that. Anything exam-related. Okay. Let's do that. Let's go over here. Good to see you randomized in the chat. Let's do this here at the 4:43 mark and do Stat 201, Chapter 5, Empirical Rule questions. Oh, yeah. So let's do this right here. We're going to do empirical rule questions to start. Here we go. So, David, this is going to kind of cover what you want right there. Oh, look, what do we got going on? Let's take that off screen. Okay. So, in this first question, is a Chapter 5 empirical rule question. What numbers come to your head when you hear the empirical rule? What numbers come to your mind when you hear the empirical rule? What numbers come to your mind? And we have a Kahoot later today at 4 p.m. I was like, let's do a second Kahoot. I want more people to come to the Kahoot. You got this, Adelaide. Adelaide, we're here to practice. You got this. What numbers come to your mind when you hear the empirical rule? And here's the thing. They're written on the test for you. So if you don't know them right now, if you get them wrong, you can check the test. We got this. We got this together. Don't worry. We're going to do this. We're all in this together. 1,000 points right there. Good. Ooh. David's breaking it down to even more. The 0.15, 2.35, 13.534. So don't cram the material. Do it in. Study in. We all know. Little bits. So we got a Morbin. You got this. We know what's going on. We're going to Morbin. We're going to get this right. So a question might say, use the 68, 95, 99.7 rule to solve. So if a question says this, and it probably even bolds it like that, you will use this. Good to see you, Aaron, there too. Does everyone understand what I'm saying? Is like there are questions that are written this way. There are questions that are written this way. So I'm going to write you 3 questions. I want you to solve each of them. You ready? So a test is given to students where the average is 70 with a standard deviation of 10. Solve all 5 questions below using this rule above. And let's say the following. So percent of students above 70. Percent of students below 60. Percent of students above 60. A few of these I'll try and remember. Percent of students below 40. Percent of students between 50 through 70. That should be 70. That's a tougher one to do, 80. Okay, and that's question 4 still. Okay, can you solve how many of these? So what do we try to do if we get a problem like this? If you get a problem like this, what is the first thing you should think about doing? As Joey said on Full House, what is the first thing you should think about doing here? If you get a problem like this, what do you think about doing? What do you think about doing? Draw it out. So we go right here and we draw the normal curve. So we draw the normal curve. And with this in mind, we go right here and we go 1, 2, 3 standard deviations up and 1, 2, 3 standard deviations down. And we can do the z-scores and everything, right? So you're going to go here. And you can answer these questions in the chat if you want. I'll draw out what I'm doing, make it very clear that we are going standard deviations up, standard deviations down, and then we put the z-scores below it. So before I even usually read questions, I start drawing this out. This is how an empirical rule question could be asked. So you want to go up and down the standard deviations. And so you put at the center of the curve, you put we'll go nice light blue. You go 70 is at the center. We morb in. It's a saying for lock in. It means lock in, but we morb in here. So I guess we morb in. It's just a fun term for lock in. So it's instead of lock in, morb in. Does that make sense? Randomized. It's just a fun way to say it. I'll play the morb thing again. I should put it over on this screen. Actually, I can. 2 seconds. Because we didn't get copyright claim for that. Oh, there we go. Oh, did I do it? Yeah, here we go.
Let him cook! Let him cook now! Let him cook! I said let him cook!
It's morbid time.
There you go. You're cool. You're cool like us here. Morbin time. So hopefully we don't copyright claimed. First one is 6. Well, it says the first one says percent of students above 70, right? So you always want to draw it out. So what percent of students will go to the orange right here? What percent of students are above 70? So you go to 70 and you go above it. So what percent of students are above 70? What percent of students are above 70? The first one right here, percent of students above 70. Yeah, you see it. Yeah, daily 30 some points. Once you're like, oh, it's the middle of the curve. So you see it. Great job, William, Aaron, and Daniel. You see it's the middle of the curve. You're like, well, of course. Once you see it. So you always want to do your drawings. This is, remember, draw it out. If you're practicing with me right now, draw it out. It's much better when you can draw it out. So now, what do you think is the percent of students below 60? And you can guesstimate these, but you can get the right answer. So try to solve it. I'm going to show you the math right here as we solve this. Here is the math for the answer below 60. It's going to be like this. And then you have 68. And what is the answer? So this is the second one we're doing right now. We're doing the second one. Because 68 is according to the empirical rule at 1 standard deviation. Well, you're probably thinking 34 is the area between here and here. And it's not 34, though. And David has it if you add up all the numbers, because there's 0.15, 2.35, and people are saying 16. Yes. And then this is 13.5 if you go through and get all the numbers, which we didn't do, but you can do that. And then you have to make sure they all add up to 16%, because what you do is you do the inside-outside trick. That if 68% is inside, 32 is outside, and then it's half of 32 is 16. So you have to make sure when you ride the rails right here that you add up to 100% if you go across the whole thing. So now it wants the area above 60. So using our answer from 2 that we just found, remember that it's no, Aaron, you got this. Draw your pictures. Draw your pictures. So now we're on question 3. What is the area above 60? 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 Not 94, though. 84. Yeah, you might have mistyped. Mistyped right there. Good work. Yeah, don't worry. That's good answers. Let's throw you some points. It is 84%. And you know how to get it right now. You're seeing it. It's just the complement. It's the other side of it. So if 16% is below, then 84% is above. Now it wants the percent of students below 40. So who knows the percent of students below 40? That's going to be right here. We're on question number 4. And the percent of students below 40, it's going to be this little tiny thing. Percent of students below. We got a lot of interesting answers. Everyone confirm your answer. So think of the number you're going to use. You're going to use this number right here because that's 3. It goes 1, 2, 3. And so you're going to go here and say 99.7%. And then you do the outside trick. And it's going to be, can type the answer again if you want. Who can type the answer again to confirm the answer here? It is 0.15. 0.15 here, 0.15 here. What do you do to confirm that you've done this correctly? What do you do to confirm that you've done this correctly? Who remembers what you do to confirm that you've done this correctly? You make sure this what's. You make sure this what's. You make sure that that all adds up to 100%. Adds up to 100, exactly. Now, this next one's not that bad if you see the trick to it. It wants the percent of students between 50 to 70. Who thinks they have a way of getting this one pretty easily? 50 to 70, how would we do this? Between 50 to 70, what's a trick? And the trick is this, if you think about it. What is the trick? There's multiple ways to get this. That's one way, David, you got it. You can go 13.5 and 34, and adding those up gets it. And then Rose has the other one, 95 divided by 2. So either which way, you're going to get 47.5 as the area for that portion right there. Yeah, if you just cut, and that's what I was drawing, like that's another trick, or add up the areas. But this is the empirical rule type questions where you have to use the empirical rule to solve. So does everyone see, like, it? When do you know to use these numbers? The question will tell you. Wow, that's a cool design. So the question will literally say, use these numbers. The questions will literally say, use these numbers. But there's another type of question where you get a picture. So people are really afraid of these questions because they're like, wait, some of them are going to give me pictures. So let's do section 1, chapter 5. Normal curve drawing questions. So I'm going to do 4 levels of question, each time getting more difficult. Does that make sense to everybody? Each question that we do right here is going to get more difficult. And we're going to use the same concept of a curve with a mean of 70 and a standard deviation of 10. So each of these is going to get progressively more challenging on my quiz right here for you. So get ready. The first question is going to ask you, what percent of students, I haven't written it out yet. This is an easy one. This is one I want you to get, okay? So what percent of students scored below an 88? What percent of students scored below an 88? See if you can solve it. So we're going to take a picture here. What percent of students scored below an 88? It's the same information as the previous questions. What percent of students score below an 88? So this tells you where it's marked. Well, 88's right here, right? So 88 is right there. Yeah. And we want below an 88. So we want this area down here. Close, close. Use the graphic, though. Close. So, close. Because it's saying to you that this... Yeah. This is 4% of the data. So, the other side of it would be the 96%. Do people follow this one? So, 4% are above an 88. 96% are below an 88. That's a level 1 question. And we don't expect you to use the empirical rule for this. We expect you to use the pictures. So this one is, Aaron, do you have a question on this? Let me know if you don't get it, just because I want to go each level making it more difficult. And I'll do some really tough ones near the end. Like, you can tell me I don't get it, or can you go into more detail? Yeah, you get it. Nice job, Aaron. 1,000 points right there. Good to hear that. Yeah. Thank you for commenting everything. I want to make sure people are following along as we do this. So this next one's going to be a little bit more difficult. Next one's a little bit more difficult. Do we disregard the normal curve for these? Oh, this is the normal curve. But this normal curve is doing it more exact. If it doesn't say... So when do you use the... When on a question do you use the 68, 95, 99.7 rule? Repeat to me again. When will you use this rule right here? When will you use this rule? You'll see... When do you know to use this rule? You will. So when do you know to use this rule? When the question says it. When the question says, use this rule, use this rule. If the question gives you a picture, what do you use the rule or the picture when the question gives you a picture? If the question gives you a picture, what do you use? I know. You're like, once you say it, you'll be like, oh yeah, that makes sense. You use the picture, exactly. So just making sure everyone knows, because that gets you in line with the question. Like, you see this picture, like, I mean, it still follows the 68, 95, 99.7 rule. But it does more exact calculations. It's more exact than the empirical rule, because the empirical rule is rounded. If the empirical rule wasn't rounded, it'd be 68.26, 95.449, and 99.7300. But there's even more decimals than that. Yeah. So here's a level 2 question. With this level 2 question, the question now says, you're welcome. That's what the question says. What percent of students make above a 85? What percent of students make above an 85? Okay. What percent of students make above an 85? Dang it. Great job, David. What percent of students make above an 85? You're starting to get it. You're getting the tricks. So when you look at this right here, think about an 85. Let's say someone's stuck. What suggestions would you have for the person who's stuck? They should turn 85 into a what? Like, if you're stuck on... What's a good thing to do to 85 that you can just do to be like, put 85 into a... Make it so it's the same no matter what. Turn 85 into a what? Turn 85 into a z-score. So you do observation minus mean over standard deviation. And draw it out right here. 85 minus 70. This is observation minus mean over standard deviation equals z-score. And so we're going to do our 10 equals 1.5. So that means you'd be over here on the curve right here. And I think everyone noticed that it's symmetric with the other side. Oh, wait a minute. Did I say... What was my question? Who... Oh, no. Uh-oh. So I think people did the reverse. What do you think the answer is now? Because this is where an 85 is at. And it's the percent of students above this. So what is the percent of students above it? Double check your work. It is 7. It's literally just a flip of this curve. because this is a z-score of negative 1.5, you could do 55 minus 70 over 10 is negative 1.5. So this is just, do people see it? Tell me if you don't follow it, but you can just flip this curve to the other side and you would get the other side of it, like as best I can draw. So you just flip it like that and it goes to the other side. So it is the 7% on the other side of it. 93 is the percent of students who would make below an 85. Below an 85 is 93% of students because you'd shade the other side of the curve. You'd shade to the left of this, and this is 7%. So it's 7% on that side, and it's 7% on this side when you do the above. Any questions on this one? This was like a level 2 question. Trying to make them each one a little bit more difficult, little tiny bit more difficult. Working those little bits right here. Okie dokie, as they say on Fallout. So now let's make it more difficult. We're still working with a mean of 70 and a standard deviation of 10, but tell me this. A student who scores in the 80th percentile scored a what? A student who scored in the 80th percentile scored a what? I'll write it out for you so you can read it. Oh my gosh. A student who scored in the 80th percentile. Good to see their tie. A student who scored in the 80th percentile scored a what? So let's write it out. The curve has a mean of 70 and a standard deviation of 10. A student who scored in the 80th percentile scored a what? Anyone stuck on this? What are your thoughts? What does percentile mean? Like if you're in the 99th percentile on a test, what does that mean? What does percentile mean? What does percentile mean? The amount of data where to what? What does percentile mean? What does percentile mean? Dolly Parton for president. Everyone loves Dolly. She's amazing. What does percentile mean? Take a guess. I'll tell you if you're right or wrong. Don't worry. We throw points here. Not kind of rang. Okay. It means the amount of data below you. Below you. So do you want to be on the first percentile on the test or the 99th percent? Rather, do you want to be in the 99th percentile or the first percentile on the test? Because where would the 99th percentile be? Do you want to be in the 99th percentile or the first percentile? The 99th. So that means you're at the top of the test. The first percentile, and don't worry, we'll throw you some more points here. Good job answering questions. We like answers here. And so the first percentile is down here. The 99th percentile is over here. Does that make sense? The 99th percentile is on the right side of the curve. That would mean if you're at the 99th percentile, 99% of the curve is below that point. So when you talk about the 99th percentile, 99% of the data is below that point. So what information are we currently given? Very clear to see. We're currently given a what? What are we currently given? We currently see the what? I mean, it says what it is. And it's pretty obvious from down here. We currently see a z-score. What does a z-score tell us? What does a z-score tell us? Which I think Ian's kind of got the answer. Throw another decimal. Ian's right for 5,000 points. We'll throw some big points. Ian got it. Good job, Ian, right there. What do we do with a z-score? I want Ian to carry one more decimal for me. What does a z-score tell us? Well, a z-score tells us how many standard deviations we need to go up. And is it 0.84 is the answer? Well, that's not the answer. Great job, Ian. Yep, Ian's right. And it's somewhere between 70 and 80. Does that make sense? Who understands and follows me right here that this at a z of 0.84 is between 70 and 80? How many standard deviations do we go up and down from the mean? Correct. And so the answer must be between 70 and 80. So you would take the formula of z equals observation. Oh my gosh. When you do that, it rezooms out. So you got to do this, and then there you go. So you take the formula of observation minus mean over standard deviation. You rewrite it so that you're solving for the observation, which is the observation equals the mean plus the z-score times the standard deviation. That's just a reworking of that formula where you're solving for y. So now you can put in the mean of 70 and put in the z-score of 0.84 and times it by 10 and obtain the value of 78.4. And what's great about these problems is if you work them out, you can go to the applet and you can even check your work by going in here and doing the following, and you can see the answer. It is carrying one more decimal, but there's the answer right there. Okay, now let's do a really tough problem. You ready? So now we're going to do a really tough problem. I mean, really tough, it's relative. It's all I'm just adding more tricks. You scored in the top 1% of the curve. You scored in the top 1%. What was your score? N percentile. You scored in the top 1%. What was your score and percentile? This is a good review question for concepts we've been practicing. So on a test with a mean of 70 and standard deviation of 10, you score in the top 1%. What is your score and percentile? Okay. So once again, we are given what's. Tell me if you're stuck. We're doing question after question, and we can do another concept right after this. Does anyone know what, if you're in the top 1%, what is your percentile? If you're in the top 1%, what is your percentile? The 99th. That would mean that 99% of the curve is below. 99% of the curve is below. And this is 98 in the center, and this is 1% outside, which means that this is the top 1%, because if 98's in the center, symmetrically, who follows me that, and already Aaron's got the answer. Nice job, Aaron, because you know you do z-scores. So that spot is where the 99th percentile is at. Like, this is the 99th percentile. And with that, we know its z-score is equal to 2.33, and it's the same solve from there, because now with a z-score of 2.33, all we do is take and do that the observation equals to the mean plus the z-score times the standard deviation. And the observation is 93.3. There we go. And that is equal to the mean of 70 plus the z-score of 2.33 times 10 right there. Did I do this one too quick, or do people follow? We did a lot of these, and I hope they're making sense. Like, these are ones where you have to use the picture, and drawing on it helps. And I feel like people, please tell me if you're stuck or if you want me to do an easier one. But man, I was impressed with that. A lot of answers. If you start to draw on it, you start to draw it out, it makes more sense. I know I've done a lot of these. I've been solving these problems for over a decade, 15 years. So yeah, what chapter do you want to cover, or do you want more of these? Take your vote. What do you want? First vote, or we'll wait for 2 votes to come in of the same thing. You tell me what to cover, we do it. We'll wait for 2 votes of the same thing. Because the z-score is because Adelaide, good question right here. Do you see the question tells us, if we start from the beginning and we'll wait, Scatterplots, we can start doing that. Up. 2 votes for Scatterplots from David. So do you see the question says there's 98% in the center. Up. Chapter 6 wins. Does everyone see 98% in the center? So if 98% is in the center, how much is in each tail? How much is in each tail? Yeah, no, thank you so much. Adelaide, thank you for asking. 1,000 points right there. Then we were able to deduce that since this is true, then it must be that this is the 99th percentile, because 99% is below there. So that's how we got that being the 99th percentile. Okay. Oh, p-values. There's some p-values. So we do chapter 6 and chapter 5, do some scatter plots, then go to p-values. So let's talk about correlation concepts and ideas. You're welcome. And once again, when we're on these topics, just ask all the questions. It's really awesome. I like helping out. So thank you, everybody here. Okay. And thank you, visitors from other classes, chilling out. We always want you here. I wish we could make your points worth something, but maybe say, be like, Terry, ask Brian how many points I got. He can do whatever he wants with them. It's his class, his call. I could be like, oh, they did this. It's his call. He would need to rewrite his syllabus and let students know, but I can always tell him. I appreciate people checking this out. Here we are with chapter 6. Chapter 6 is going to be over scatter plots and correlation. What are the 3 conditions 3 conditions to do correlation. And what are the 3 conditions? When do you do correlation? Does anyone know? When do you do correlation? Tighten this up every day. When do you do correlation? QQ, straight enough. Nice. I like that. Randomized. Let's start with 5,000 points randomized saying that. QQ, which stands for 2 quantitative variables, not qualitative, straight enough. Does it follow a linear pattern mostly? QQ, straight enough. No outliers. Are there no outliers? QQ, straight enough. No outliers. I say QQ because it's a lot easier than 2 quantitative variables, straight enough. Doesn't work. QQ, straight enough. No outliers. And then we'll have plot doesn't thicken coming up later on. So with this in mind, how do you check if it's 2 quantitative variables? Like, how do you check 2 quantitative variables? How do you check 2 quantitative? I'm going to open up R real quick. R Studio. How do you check 2 quantitative variables? How do you check that? I'll even talk over how we try to trick you on the test. Untitled 2. You just look to see if 2 numbers. So let me load up. I love coding. How about this? Is this 2 quantitative variables? I'm making graphics. Really? I messed up. There we go. Fix it. And is this 2 quantitative variables, yes or no? Now be careful. I want you to look at the variables. Look at the variables. The graphic I'm really looking for is this one right here. Is this 2 quantitative variables, yes or no? Is this 2 quantitative? Yes or no? Just yes or no. Is this 2 quantitative? No. What is this graphic called? The X is categorical. The Y is quantitative. What is this graphic called? Anyone know what this is called? It's one cat, one quant. What's it called? We are over here in this world. So what's this graphic called? Genders side-by-side box. And think about it, it's box plots, and there's side-by-side.
Wow.
So yeah. How about this graphic up top, not the bottom one? How about that graphic? How about this graphic? What graphic is this? It's kind of mosaic plot, more mosaic plot. Sorry, randomized. This is a mosaic plot or kind of a stacked segmented bar chart, whatever. It's going to be down here in this corner where I was in the image. It's a mosaic plot. I think randomized. Randomized. I'll lock in. And then you see a contingency table right here. So watch this. Let's go here. And now, is that a scatter plot? Do not confuse it with a dot plot. Is this a scatter plot or 2 quantitative variables which make a scatter plot? It also has what's called border histograms, but this is a scatter plot. A dot plot is when you just have dots like this. It'd be like the histogram, but with dots. So this is a scatter plot. Like this is a scatter plot due to QQ. So what does it look to be mostly straight enough? It's debatable. It's debatable if it's straight enough. Like statisticians might argue that there's a little bit of a bend. Does everyone see what I'm getting at here? A lot of data isn't straight enough a lot of times. But what seems to be a major problem here, which you'd point out? You see how we're saying it might have a problem with not being straight enough because it kind of bends? It definitely has a problem with what's though. It definitely has a problem with what's is. Things that break the bivariate outliers. The chat is sometimes I don't even know what to say to chat. With this right here. So with these questions, and what we mean by that is like when we do regression or when we do correlation, it only applies to what relationships. And this is so very important. Like you bring up a good point right there, randomized, very random today. What is the correlation of the graphic on the left and the graphic on the right? So I'm about to hit some really good true falses on everyone right here. What's the correlation of the graphic on the left? What is the value of R right here? What is the value of correlation right there? What's that correlate? Just guesstimate it. What is the value of correlation? What is the value of correlation there? 0. R is how we assign the value of correlation. And the value of correlation right there is probably super duper close to 0. What is the value of correlation here? Who knows the graphic on the right's value of correlation? The graphic on the right, it's also 0. Correlation only measures linear strength. Correlation only measures linear strength. If something has a correlation of 1, it must perfectly do what? Things with a correlation of 1 must perfectly do what? If it has a correlation of 1, it must perfectly what? If something has a correlation of 1, it must perfectly what? And go up. So it must go up and perfectly follow a line. Perfectly. If it's -1, it perfectly follows a line and goes down. Can things have relationships but have correlation of 0? Yes or no? So yes or no. Can things have relationships and have a correlation of 0? Because our correlation only measures linear relationships. Yes. And so when you do correlation, you can kind of go around it. And if it looks more like a 0, it's closer to 0. So that looks like a 0. If you go around them, they all look like zeros, but these all have relationships. They're just non-linear. You only measure the linear strength of the correlation with how tight it is around a line. Strength is tightness around the form. And so you can see the strength right here with how tight it is, where this is kind of moderate weak, this is non-existent, moderate weak, moderate strong, and super duper strong. So this is a very strong relationship here because it's tight around the sinusoidal form, and this is tight moderate because it's moderately tight around a parabolic form. Does everyone understand right here? What are the 4 ways? This is good. I'm hitting tons of questions if you can't tell. I know I'm going a little fast, but tell me to slow down. What are the 4 ways to describe bivariate quantitative data? What are the 4 ways to describe bivariate quantitative data? So if you have a scatter plot, what are the 4 ways to describe it? What are the 4 ways to describe a scatter plot? It can be, I see strong, or strength, strength, direction, form, unusual features. So strength, direction, form, unusual features. And what are the 3 ways to describe a histogram? What are the 3 ways to describe a histogram? What are the 3 ways? With histograms, it's quantitative data. So this is just like height, weight. This is height and weight, like height and weight, where this is just like height. You're just analyzing height. This is analyzing height versus weight. Shape, center, spread. Are light bulbs going off in people's heads right now, being like, oh yeah, the shape of it, the center of it, the spread of it. And so when you do histograms, we'll start with histograms because that's just one quantitative variable. It'll either be more normal for skewed or more normal. If it's more normal, for center, we'll use the mean and we'll use the standard deviation for spread. If it's more skewed, we'll use the median and the IQR. So that's what we use right there. For strength, it's either going to be like closer to -1 or 1 is strong and closer to 0 is weaker. The more spread out it is, the weaker it is. So this is like a really strong relationship, and this is a really weak relationship spread out. For direction, what are the two directions it can go in? What are the two directions it can go in? So direction, when we think about direction, it's really just like this, or like this, or like it might go in neither. So it can go in positive, negative, or neither. And up or down, positive, negative, or neither. The form is either going to be what or what. The form is what it follows, like the pattern it follows. That's what form is. So it's either a line or not a line. Very easy right here. It's either a line or not a line. And unusual features are just outliers. So when you do a drawing right here, unusual features would be like this thing down here. And that's the unusual features down there. So that's an unusual feature. Is this making sense? Strength is going to be how tight it is around the form. So you look at the tightness. I love asking this sort of question. Which of these is stronger? Don't hit A or B yet. But I want to know which start a poll. And let's say which is stronger. A or B. Don't hit A or B yet. Which is stronger? Which of these is stronger, A or B? Does anyone want to explain in the chat? It is B. Strength is tightness around the form. Here's the form. I drew the form in the middle of it. Sometimes you get things like that. And you can see the strength is going to be, if you put bands around it, you can see this is tighter around it. So this is much tighter than this one right here. So B is definitely stronger than A. The points are closer, but it's nonlinear, exactly. So which of these is stronger correlation? Now be careful. So I'll just ask in the chat, which is stronger correlation? Stronger correlation is going to be here probably with an R equal to about 0.6. And over here, this probably has an R about 0. So, shout out to Randomize right there. That's awesome. Okay, I gotta tell you a joke story after this. Here, I'll tell you a funny story. Shout out to your boyfriend. Tell him, hey, Randomized boyfriend, you rock. You're learning stats right there. Strength is the tightness around the form. The form doesn't have to be linear. So if something says like, can you have correlation of 0 and have a strong relationship? Yes or no? Yes or no? Can there be correlation of 0 and have a strong relationship? So can there be correlation of 0 and there be a strong relationship? All you have to do is look at this graphic. Yes, it's just nonlinear. Correlation only measures linear strength. So it's the strength around the linear form that correlation measures. So you can have that. Okay, so very quick story time with Brian, and then we will go to the next topic. So also, tell me the next topic you want to do. We could do p-values or something else, but tell me the next topic. We probably got time for at least 2 more topics, but that was kind of a whole scatterplot intro. We covered a lot of... I know what the test looks like. That covered at least 5 or 6 questions on the test. And very directly, especially the last thing I was on. Okay, so story time with Brian real quick. When my wife and I lived in College Station, the people who lived below us, like literally in the floor below us, was this lady, and she had a child, and the child was like a year old or so. And the child was a year old when we got there, and by the time we left, the child was 4. But I would broadcast class from, we believe, the broadcast room I had was, we think, above the child's bedroom. Because like we had the big bedroom, and then there was the second bedroom we used to broadcast from. We'll do p-values next, I think. So we joked that like I taught out of that room for like 3 years, the room above. So like this child was probably hearing maybe like me broadcasting statistics and being like, the p-value is the probability of our results from our stream. And like the child would like one day say to their mom like, what are p-values? Like somehow like the knowledge had permeated through the walls, and we just joked that like maybe I talk very loudly if you can't tell. And yeah, because it's just funny to us. But that's the funniness. You reminded me of that when you said your boyfriend learned the knowledge. Then one last story also. This one student of mine would take care of her. I can't think if it was her nephew or it was all good questions here. But I was like his Mr. Rogers almost, like not literally, but she sent me a video where his name was like Isaac. And I was like, "Hey Isaac, hope you're having a good day." And we like started the class, and he's like, he's in his little bouncy chair. That made my day. Like to think that like some little 4-month-old is like watching the stats class. So that kid's gonna be a stats genius. There we go. Let's go back to doing studying. Can we do? I know. Stuff like that really is. It's why I'm here. It's literally why I'm here. That makes my day. We got some good questions in chat. Focus in. Here we go. Can we do a Kahoot review if you have one? We'll be doing one at 4 p.m. today. Come back at 4 p.m. or check it out later. We'll do a Kahoot review at 4 p.m. I get confused on the p-values for the normal model and the other ones. We'll do that again. I think that's what we're going to do next, linear or not. If you don't feel confident for the exam, what should I spend most of my time studying? Here's my advice on if you don't feel confident at this point, which is totally fine. The first exam in any class is always super scary, and then you kind of just work it out of your system. You take that first exam, and then you're like, okay, so this is how the exams are. This is what I need to do. What I would suggest is, first of all, try going through the practice test. And if you're stuck on any question in the practice test, there's a video going over every question. So on review 1 right here, you can see a video on every question. I usually try to lecture a little bit, and you can see the outlier right there. It's straight enough. It's mostly straight enough. It's just an outlier. And this is what we were just covering, the no outlier condition. You can see the outlier. I took a lot of time editing these videos so that you could see exactly what's going on. But I made some highly edited videos here going over each question, explaining the concepts with what's going on, and visually on the screen talking about the weakening of the relationship right there. You can also go over the chapter reviews. Once again, study in little bits. Be like, I'm going to watch this 15-minute video. I'm going to take notes while watching it, and then think of some exam questions. And last but not least, we can't forget to mention MuBot right here, which I want to see how many chats MuBot's been having. But what you should do is you should go check out MuBot, which I can drop his link in the chat. But he has Quiz and Learn. MuBot does. I'll drop his link right here. And if you go do this, he can quiz you on the test material. So, and I've been telling other groups about this. So yeah, MuBot, thank you so much. I'm glad people are liking him. I'm going to check out real quick, and then we'll get back to it. I always forget how do I always forget this? Oh, it's GPTs. He had 400 chats last time I looked, and he's at 500. In the last few days, he had another 100 chats with people. I am MuBot in the chat. Go to MuBot right there. And I'm so glad this is helpful. I do want a review of this after the semester. But he's had 500 chats with students so far, and I'm hoping that this works out. So try the Learn and Quiz button. You can also upload your data analytics, move out any files from it, or your names and stuff. But check it out. Good advice for reviewing for the test. Okay, let's talk about p-values here. There's not a ton of questions over these. I'm going to try to orient your knowledge. And Liz, thank you so much for those questions. So we're going to talk about p-values and hypotheses. Chapter 5 and 6. P-values and hypotheses. And then another question. And hypotheses. Does each new chat I have with them... I think it might... I think it's each new chat. So, I don't want people to open up a bunch of chats just to do that, but yeah, don't do that. I don't want to be like, you inflated your analytics. Use MuBot however you want to use MuBot. I want to know the numbers, because also it's a return on my investment, because I've spent probably 100 hours working on them. Something I don't record it, but it was a lot of the summer. I mean, his instructions are pretty big. Here we are. Chapter 5. Yeah, I am curious too. I don't know the answer. Good questions randomized right there. Okay, so this is about p-values. When it comes to p-values are a concept used throughout statistics. So be very careful. P-values are not something we use in chapter 5 and we forget, or chapter 6 and we forget, or you look at a p-value, it can mean slightly different things, but let's talk about what a p-value always means. What does the P of p-value stand for? What does the P of p-value stand for? P-values tell you what of something? it's the P of it that matters. It's a what value. Like, don't even worry about the context of the chapters yet. What does the P of p-value mean? What is the P? Randomize, that's very close. It's pretty right. I'd prefer to say probability, probability, probability. And it's not like percent, like percentiles on the curves. You can use it for things like that. But a p-value literally means, in the statistical sense, the probability of our results or results more extreme occurring by random chance variation given the null hypothesis, he already knows, is true. What in the world does this mean? Okay. So we have to do an example now to make this make sense. If no, or results more extreme. Our results, or results more extreme. So Brian claims he is a 5-minute mile runner. So if I say I can run a mile in 5 minutes, you say, let's go to the track, run a mile. What do you expect me to do? Just don't even worry about stats for a moment. If we go to the track and I say, I can run a 5-minute mile, what do you expect me to do? I can run a 5-minute mile. Don't even overthink it. I say, I can run a 5-minute mile. Well, what do you expect? I don't even know ham and cheese loanables. Should be lunchable. You expect me to run a 5-minute mile, right? If I say I can run a 5-minute mile, and think what you're saying here, this right here is a null hypothesis. The null hypothesis is just an initial claim. Does that make sense? I say I can run a 5-minute mile. So if the null is true, so given the null is true, you would say Brian is expected to run a 5-minute mile. So the most likely result is that I would run it in 5 minutes. Now, with that in mind, is if I were to run, let's say you observe me, that's an observation, me running it in 5:01, would you call me a liar? If I run it in 5:01, let's pretend on the curve right here, it's over here. Would you call me a liar if I run it in 5:01? Would you call me a liar? Would you like, you ran it in 5:01, you can't run a 5-minute mile. Kinda. Yeah, I'm gonna keep going randomized. As I talk through this, let me know if you get stuck. Let's say you observe me running in 5:01. You'd be like, well, that seems likely. So when you think about probability right here, when we say the probability of our results, let's say here, we'll put our result. Our results is this. Does everyone follow me? This is our result. If you're trying to say I'm slower than 5 minutes, a result more extreme than this, or a result more extreme would be over here. Who follows me? A result more extreme than this is over to the right on the tail. Like you say, Brian, I think you're slower than 5 minutes. More extreme is to the right of that. Like something, our result is the 5:01. That's what we saw in the data. We saw Brian running this, and the probability is going to be like, if this is, let's put this right here, the probability might be like, let's say 48% of the time this would occur. And the random chance variation is the normal curve itself. That's the random chance variation. So with this in mind, what does this mean? It means that a 5-minute mile runner would run 5:01 or water 48% of the time. Just think about what this means visually. A 5-minute mile runner, due to random chance variation on how fast people run miles, if we actually did all the data, a 5-minute mile runner would run 5:01 or water 48% of the time. A 5-minute mile runner would run 5:01 or water, because I'm thinking to the higher side of it. A 5:01 or slower, 40. So this is slower because this is a higher time. Like I know higher usually means better, like higher, or because this is a higher time, 5:01 or higher, because you observed me running 5:01. So so it's a higher time than 5:01. If you're a 5-minute mile runner, apparently 48% of the time you run 5:01 or slower. So is this a likely thing or unlikely? And I want you to pretend it's like rain today. whenever you see p-values, I want you to think about like rain. Is that likely rain or not likely rain? Like someone says 48% probability of rain today. What are you gonna do? Is that likely or unlikely? You're like 48% probability of rain. That's likely. I mean, it's not more than 50%, but it's still likely. You're like, you grab that umbrella, you say 48% chance of rain. But now imagine this. Brian runs his mile time in 1501. And that's all the way off the curve over here. So now our result, which we did in orange, is over here. And a result more extreme is this. And so now the p-value, which we did in the blue pen, now the p-value is equal to this. And think, if you're a 5-minute mile runner, running this in 15 minutes would be very, very what? If you're a 5-minute mile runner, running this in 15 minutes would be very, very what? If you're a 5-minute mile runner, running this in 15 minutes would be very, very what? Running in 15 minutes would be a very, very what result? 1501 rather. Do you think 5-minute do you think 5-minute mile runners, when they're trying, run it in 15 minutes? Look at the p-value. What does the p-value tell us about this? It tells us this is a very what result? Unlikely. Does that make sense? Like, if you're a 5-minute mile runner and you go out and run a mile, like, and you're trying, like, it's not just like you're just warming up or something. If you're like, I'm going to run a mile in 5 minutes, and you try and you're a 5-minute mile runner and you run in 15, that's not something you're likely to do. It's an unlikely result. So at this point, you would reject that Brian's a 5-minute mile runner and say we have evidence he's not a 5-minute mile runner, that he's much higher than a 5-minute mile runner. Who follows me on this example, which I think is one of the easier ways to start by understanding p-values? It's the probability of what we saw or something more extreme than it occurring by random chance variation given some hypothesis is true. So that leads us into, so I'll say p-values in general for that first part. Let's talk about p-values in chapter 5. So now we're going to hear the context of p-values in chapter 5. Chapter 5 p-values. Oh, randomized. I like hearing that. I always try to use a context that's not statistical, and then we do statistical. Because if you understand it outside the statistical idea, then you can put it to a statistical idea. Chapter 5 has the concept of the null being the data is normal. And then the alternative is what you will believe if you don't believe the null. Like, you either believe the null or you have an alternative. Like, I believe Brian's a 5-minute mile runner. My alternative is he runs slower than 5 minutes. Like, you have a different belief you could hold to if you no longer believe your null. So what do you think is a good alternative? We should believe the data is normal. And if we no longer believe that, we would believe what instead? If the null is the data is normal, what's a good alternative to that belief? Like a different belief we could hold. We could believe the data is normal, or we could believe the data is what? That's right. It's not normal. Yeah, you got it. It's either normal or not normal. That's good alternatives. And with this right here, we have two things we generally see. There's 3 ways to test. So these are the tests right here. And the first test you can do is to, as the Joker said, look at me. He's like, look at me. With Harvey Dent. Is that how he says? No, that's a different part. I think it's with Rachel. So one trick we can do. I drew like a perfect eye a few days ago. Now I've forgotten how to do it. Oh, you do this. There we go. Sure. I was so happy. If we look at it and it looks like this, is this normal or not normal? What do you think, normal or not normal? If you look at it and it looks like that, is that normal or not normal? What do you think? I mean, best I can do. It's pretty normal. And over here, we're going to do the not normal section. And then we're going to show p-values at the end of this. So if it looks more like this, or any sort of non-normality like skew or things, then it's not normal. So that is not normal. Then you have a normal probability plot. Does anyone want to explain how a normal probability plot checks normality? Normal probability plot. Does anyone want to explain how a normal probability plot checks normality? So, does anyone want to explain how a normal probability plot, which looks generally like, we'll do the line down the center. Boop. How does a normal probability plot check normality? How does it? It can be a little weird. Not like this, though. If the points mainly follow the line, they need to mostly follow the line. Mostly. There can be a little bit of weirdness, but mostly follow the line. The last one is the goodness of fit test. And this has the p-value. So with the goodness of fit test here, what we do is we see if the normal curve is a good fit on the data. So we literally take the normal curve and we add it to the data. And we're just think about what the test is called. The test is called, is this a good fit? Who follows me on why is it called a goodness of fit test? When I realized, I was like, what? Okay, so tell me, does this look like a good fit or bad fit? Just say good or bad in the chat. Because the goodness of fit test takes and sees, does your data fit the normal? Like, think about this as genes. This is the genes. This is you. Is this a good fit? Pretty good fit. Shout's Fashion Society. They say everything's good fit. I love them. And now, if you look over here, if we have another normal for this one, we'll do this one in a different color. If we have the curve here, well, it's not going to work. We're going to have to do this. Well, here we go. Let's do it. Let's take the normal curve. Let's try to fit it on it. So you can change the spread of it. Like, you're allowed to do that. You just can't change the shape of it. But if you try to fit this normal, it's not going to work. You can't fit the normal. Look at it's like breaking out there, not fitting there. So this is a very bad fit. So here's where the p-value comes into play. When you look at the p-value, if the data is normal, how should the data look? Let me repeat that question because it's the same thing as the 5-minute mile question. If we assume the data is normal, how should the data look? If the data is normal, how should the data look? It's like it's a repeat answer. If you get what I'm saying. If the data is normal, how should the data look? If the data is normal, how should the data look? It's a repeat answer. Because if the data is normal, it should look what? If the data is normal, it should look what? It should look normal, right? It should look unimodal symmetric normal, right? If the data is normal, it should look normal. So tell me, is this a likely thing to see or unlikely? If the data is normal, is this likely or unlikely to see? What you see right here, is this a likely or unlikely result? Like, you see that and you're like, oh, that looks... Then I got one more question. It's likely. So the p-value is going to be high or low? Is this fit a high or low p-value? Which one is it? Is it the high or low p-value? It's high because likely. That's what likely means, high probability. So this one has the low probability because if the data is normal, this is unlikely to see. Who follows me? Like, if the data is normal, this is unlikely to see. So low p-value and does not follow the normal model, which is that right there. Are people following me? There's not that many questions over this, but it also helps with later in the semester understanding that we have 3 different ways of doing it. You can look at it to see if it follows the normal. And the null hypothesis, which we start out believing, I'm a bit confused how we know it's likely, like why normal data. Oh, because we assume it's normal. David, such a good question. It's like, would you say, well, how do you know Brian's a 5-minute mile runner? You could say, he told me. I'm not saying he is. I'm just saying if he is a 5-minute mile runner. So if you look at the definition of a p-value, it's the probability of our results given the null is true. So the p-value assumes right here that the null is true. Does that make sense, David? So the p-value says, well, if the data is normal, it should look normal. So how likely is what I saw in my data? Like, you're not saying Brian is a 5-minute mile runner. You're saying if he is a 5-minute mile runner, what would the probability of him doing this be? So we're saying if our data is normal, This is a likely thing to see because we can actually mathematically figure out the probability of this occurring. Like, is this a probable distribution given a normal? Yeah, that's very probable. Is this a probable distribution given the normal? No, that's a very improbable distribution to see. Like, you shouldn't have data that looks like this if it comes from the normal. Like, this is very I mean, it could happen. You could have just gotten a really weird sample, but it's very unlikely. Like, imagine the sample you'd have to get that would cause this. Yeah, p-values are a big concept that a lot of people don't understand. And yeah, well, you know what? We're going to do one more concept on p-values, then we'll take a quick walk. With our last concept on p-values here, 106.23. This helps for later in the semester. Like, there's not too many on this test on it, but it's a huge help for later. Correlation p-values. So p-values. Okay. So the closer data is to the normal curve, yes, well, for this, because if it follows the normal curve, that's a more likely thing to see given the data is normal. But guess what? Now in this chapter, we're going to have a very similar thing for chapter 6, but we're going to change the null hypothesis, which is what we do in statistics. We have different null hypotheses. I'm going to keep the look at it on the screen. Doop. So here we go. So in chapter 6, the null hypothesis is no correlation. So if the null is no correlation, what is the alternative? If the null is no correlation, what is the alternative? So if the null hypothesis is no correlation, what's the alternative? So if the null is that there's no correlation, what's the alternative? Correlation. Mm-hmm. I know it's weird that the other one is that there's normal data and the alternative is not normal. Here the null is no correlation. It used to trip me up till I memorized it just a bunch of times. So with this, you can look at the data. And you can also get the R. So let's get the correlation value. What is the correlation value for that plot I just drew? What is the correlation value for that plot I just drew? R is close to what? Which is the value of correlation ranging from -1 to 1. What is the correlation value likely for that plot? Yes, the closer it looks to the null, the more likely it is given the null is true. Yes, David, you're on the right track, David. Good answer. I think that's you're starting to you're like, you'll see it on this one too. Maybe it makes sense because you can have different nulls for different tests. Like when you do a different test, you do different things. Like this test is that there's no correlation. So you might see where this is going because what we're doing is here. How about this data right here? What is I'm cheating by doing that. What do you think the correlation is for this data? And careful, they're not all on the line, so I don't want a certain answer here. Be careful, they're not perfectly on the line. They're not perfectly on the line. That's a hint for what I don't want. So guess the value of correlation for that. Cool, I like that. I'm going to go a little bit higher, but you got that right there. We're going to go R equals... I'm going to go between it. We'll go about there. Somewhere like that. Exactly. I didn't want 1 because the only way to get a correlation of 1 is if you draw the line and put the dots going right through it. So the dots all have to be perfectly on the line or correlation isn't perfect. And so now we get down to the test. So here is examples of no correlation. And here is examples of correlation. And we would run the test, so you get the number. So which of these is going to have the high or low p-value? Which of these, is it the first test has the high? Which one has the high p-value? Which one has the low? Remember, the p-value tells us what is likely to see given the null is true. So which of these is going to have the high? Which of these is going to have the low? The first one has the what? I think you got it, David, but the first one has the what? First p-value would be what? Yeah, first one's high because you'd be saying this is a likely result. So it means this is likely to see given the null is true. So the p-value is actually 1 here because you got exactly the null. Because what is the most likely thing to see if there's no correlation? The most likely thing to see is what? Just repeat it again because this tells you the probability. You just saw the most likely thing. That's what a p-value 1 means. You saw the most likely thing to see. You saw the most likely, yeah. And if we go to our example with Brian, if you were to say, Brian, I think your time is different than 5 minutes, what would have a p-value of 1 if Brian ran his mile? I kind of said the answer. If you think Brian might have a different time than 5 minutes, what would be the most likely thing to see? Alternative, Brian is not a 5 minute mile runner, 5 mile runner. What would have a p-value of 1 here for this, what we call a two-tailed test? We'll just think, what's the most likely thing to see? If Brian's a 5 minute mile runner, the most likely observation is, who follows me that this would have a p-value of 1? The most likely thing for Brian to do is running a 5 minute mile. And then that would have a p-value of 1. You would shade the whole curve, because when you say you're not a 5 mile runner, that would be outside of this time. Like something more extreme is something away from it. So this test would lead to a p-value of 1. You'd say Brian did the most likely thing. So this p-value over here is an unlikely result. And with this unlikely result, it'd be something like this. Like, is it possible that there's no correlation here? Just answer me. Is it possible that this data on the right has no correlation? Is it possible that this data right here has no correlation? Is it possible? Because remember, the null is that there's no correlation. We're saying the probability of seeing this given the null. Is it possible that there's no correlation here? It's possible, but it's like winning the lottery. Like probably even lower than that. Like I've seen p-values that are like 100 zeros. This would have a p-value so low that, yeah, R starts to calculate p-values of like basically 0, it'll say. I'll get you a p-value here. Here we'll do core test, right? Is it core test? So height, weight, and it uses commas, I think, so I didn't do it right. And the p-value is this. The p-value is 0.12345 6 7 8 9 10 11 12 13 14 15. There's the p-value, which I think it's the lowest one it generally shows. But that's the p-value right there, saying it's virtually impossible that this data would have this by random chance. So the p-values tell us if what we observe is likely by random chance or what we observe is unlikely by random chance. We would think that there is a significant relationship here between height and weight. And actually, this is a permutation test of the p-values. Not going to get into that. Not going to get into that. But yeah, I think that's got it. Any last questions to end off this review session? We did a lot of chapter 5, a lot of chapter 6. Thank you, everybody. Busy time. Busy time. Oh, yeah. I need to send out a little chill music right here. How do we access MuBot? Here we go. Let me go to MuBot. Wait, never mind. Videos. Okay, let me go. And also here is the previous. Oh my gosh, what's going on? Here's the previous Kahoot. It is a new link. I have to update the video. Okay, with that, it is time for office hours to end. I will see everybody in class or at the Kahoot. You're welcome, Aaron, so much. Thank you so much. I'm doing like 50 things. Until then. Here, wait. I got to make sure I don't play something that gets us copyright claimed again. Here, let me go. Here, we'll do a fun outro. We'll do this outro. Bye for now, everyone. Bye.